So before you start with the project tasks, let me give you a tour of the student version of the code. You will already be familiar with the basic structure as it has been built on top of the midterm project. And I suggest that you grab a copy of the program schematic and look at it while we go through the code. So let's start. So the basis of this code is basically the midterm project. So you should be familiar with many of the structures and includes and also initializations we have been using previously as well. But let's start from the top. So we have a whole bunch of includes, including STL includes as well as OpenCV includes here. And also we have our proprietary includes, which are basically the different parts of the projects which are concerned with 2D matching, object detection using YOLO, processing LiDAR data, and also performing fusion between LiDAR and camera data, which is all in camfusion.cpp. So let's start with the main program first. So the first thing which we do here is we initialize the variables and data structures which we need for our project. The first is the data path. It's currently relative to the location of the executable. Then we specify the image base path, which is and also the image prefix, which is currently set to the kitty dataset. That's the highway scenario with the preceding vehicle right in front of us. Image-02 means it's the color version of the image, not the grayscale version. I think in the midterm project we have been using the grayscale version, but now we are using the color version. Then we are specifying the start index and the end index, which is currently set to 18. Step width is a new variable which you can use to play around a little to decrease the frame rate. So currently frame rate is set to 10 images per second, but we might skip every second image just to have larger disparities between key points, or maybe to see how matching can be performed if the time in between two instances increases. So you can play around a little bit. But currently in this project, step width is set to 1, so we are using every image. Then we specify the base parameters of YOLO, base path, classes file, model configuration file, also the model weights. You have been using those previously. Then we specify the LiDAR point data, the prefix, as well as the file type. Then we load this whole bunch of calibration information, which you already know from one of the previous exercises. Basically, it's the intrinsic camera calibration matrix, the rotation matrix for relating left and right camera of the stereo setup in the kitty vehicle. Then we have the extrinsic information, which is rotation and translation. And these are all the numbers which I took from the kitty camera calibration file, which has been shipped with the image sequence we are using. If you want to use another sequence, please remember to replace those with the respective calibration files, which are in the same file folder. When you download and extract one of the kitty sensor setups or sensor sequences, you will find the calibration files there. Okay, so what else? We have some miscellaneous variables here, which is the sensor frame rate, 10 Hertz, scaled by the image step width. So if we go down to, let's say, only every second image, this gets scaled down to 5 Hertz accordingly. Okay, data buffer size currently 2, and this is the data buffer which is going to hold all the data frames which we will assemble in the following. This visualization variable here, it's always set to false, and my suggestion is to set it to true only at selected positions in the code. If you set it to true here, you're going to get a display of a whole bunch of different windows, and it's a little bit hard to keep track of what is what. So I would suggest to look at all the code steps one by one and only set visualization true right in front of the respective step which you want to visualize, and to false directly afterwards. Okay, then we have the main image loop over all the images. We do load the images into a buffer. Note that here's a small difference to the midterm project. We do read the image from file here, but it's the color image, and we do not convert it to grayscale right away, but instead we push back the frame, including the color image. That's the difference. Okay, then comes the part where we detect and classify the objects. We have some parameters here: confidence threshold and non-maximum suppression threshold. Then we perform the YOLO-based object detection here, which is done in this step. And note that we are inputting a link to the data buffer camera image, data buffer bounding boxes, and the data buffer bounding boxes, they are augmented with the rectangle around detected objects. So that's that's basically the output of the detect objects method. We are adding in rectangles into the bounding boxes here. In the next step, we are going to crop our LiDAR point cloud. Well, first of all, we're going to load the LiDAR point cloud from file. Then we are going to remove some points based on some spatial properties here, crop LiDAR points. Currently, the code is set to have a min z, a min height value above the road surface of minus 1.5 meters. That's slightly above road surface. If you had a sequence with an incline when you are driving up a steep slope or something like this, or a very deep pothole, so to speak, or a bump on the road, then this would lead to errors in the TTC computation later on, because by doing this very simple cropping here, basically what we do is we assume a level road surface. And if the reality deviates strongly from this assumption, we would have to take different measures to avoid using points from the road surface as obstacle information, but this leads too far for this course. So I'm just mentioning this because I want you to know that the working assumption we are having here is that we are assuming a level road surface for the sequences we process here. Okay, the max z value is minus 0.9 meters. Into driving direction, we start looking onwards from 2 meters up to 20 meters. And in Y, we are looking to the left for 2 meters and to the right also for 2 meters. And the minimum reflectivity has been set to 0.1 in a range between 0 and 1. 1 is the highest reflectivity and 0.0 is the lowest reflectivity. But it's still a point which comes back. So 0.0 does not mean there's nothing coming back. It's still a valid point, but only the reflectivity is really low. And we are focusing on the ego lane here. So the goal is to compute the TTC and not to display all the objects. We are focusing on the ego lane. If you want to include a left and right lane and also look a bit further maybe, you can of course play around with these values here, but for the point cloud based TTC estimation later on, we have to focus on the ego lane. Okay. Then we push the LiDAR points into the data buffer, and then we move on to clustering the actual LiDAR point cloud. We have discussed this function before, cluster LiDAR with ROI. The shrink factor relates to the bounding box or the region of interest size of the returned YOLO objects. We are making it a bit smaller by 10%. Just to avoid that points from unrelated objects creep in over the corners, over the boundaries of the rectangles, which are almost all the times when you look at the objects, they are a little bit too large. So we shrink them here to avoid this from happening a little bit. Then we have the first visualization here, visualize 3D objects. So actually, if you set bvis to true right before, then we will focus only on showing the 3D objects, which is a display which you already know from the course lectures. You saw a screenshot of this wide top view perspective with all the 3D objects visualized as rectangles with some added on information. You can run this code and set bvis to true, and then you will get the same visual as you saw in the lecture as a still image. Okay, that's basically about it. That's the state of the affairs, so to speak, right before the midterm project actually starts. The goal of the midterm project is to have you track 3D objects over time. And what we get until this point, we create 3D objects for each time step individually. And if you just want to run the code and see what's happening, you can execute it. And at this line here, we basically spare out the entire stuff which happens right afterwards from happening. So we can only focus on creating 3D objects using object detection based on YOLO and clustering LiDAR points. If you want to move on, you have to comment out this continue statement here, and then we progress to the actual part where the final project starts and revolves around. But before we get to your tasks in the final project, let's look at what's already being done here, what you already have done. So the first step is to detect image key points. This is now the step where we convert the image to grayscale. We're not doing this for the YOLO-based object detection. Actually, the results for the deep learning framework are much worse if we only input grayscale image. It has been trained with color, and if we take away the color, the results are really much worse. You can try this out and see why it makes sense to use the color image instead. But here for key point detection, we actually do need grayscale images, which is why we convert them to grayscale here. Okay, then comes the part where you can select the detector, and as you can see here, this is the student version of the midterm project. You should now have a coding framework that has much more included here, including BRISC and Harris and SIFT and all the other detectors which you were tasked with implementing. And once you download this final project student version here, you can simply copy and paste your version of the midterm into this area here, and you would have the same key point detection and tracking method as you now have in the midterm project. Okay, that's key point detection. Then we, of course, we can also limit the number of key points here, but that doesn't make much sense at this point, so I would leave this set to false. But nonetheless, if you want to visualize key point matches, you can set this to true, and this is going to limit the number of key points to 50, which gives you a better overview of what's happening. So next step is extract key point descriptors. This is also already familiar. We can select a whole bunch of descriptors here, and desk key points is inside matching 2D, the student version, and you could of course replace this function with your own code from the midterm project, which gives you access to all those different descriptors here. Currently we only have BRISC available in the final project source code. So once this is done, and we have at least processed 2 images, this is the place where we enter this area here, data buffer size greater than 1, larger than 1. The first thing we do is we match the descriptors, and here goes the same what I just mentioned. You can take your version from the midterm project and replace match descriptors with your own code, which has all the stuff implemented, which you can see here, the FLUN-based matching, and also the k-nearest neighbor-based matching, which you have been doing for the midterm project. So here comes the first assignment. Up until this point, what we do have is a set of 3D objects in space, one for each time step, and we have a whole set of key point matches between images all over the image without having looked at a single region of interest or bounding box or object yet. That has not been done. What I want you to do as the first assignment, and we're going to look into this in greater detail once we get to this respective task in a few minutes, I want you to write a function which is called match bounding boxes, which takes as an input the previous data buffer, the current data buffer, and it gives you as output a map which contains the index numbers of the bounding boxes which have been found to correspond together between 2 time steps. That's the first task. Then we write those bounding box best matches into the current data buffer. That's what's happening here. Then we move on to the next part, which is basically the computation of the TTC on the object right in front. What we do here is we loop over all bounding box match pairs which we have found. So BB matches begin to BB matches end. That's the result of your first task, which is looped over here. And this block of code here, what it does is basically it gives you a pointer to the bounding box in the current frame, the first match pair in the current frame. And this code here, by comparing bounding box IDs to all the bounding boxes in our data buffer, we get the previous bounding box. So basically, after arriving here in line 254, what you have is 2 pointers. One pointer to a bounding box in the previous frame, and another pointer to a bounding box in the current frame, and both have been matched using the method you will have implemented here in match bounding boxes. Once you have this match pair, what we can do is, or what we must do is, we must check whether both bounding boxes have LiDAR points associated to them. We couldn't do LiDAR-based TTC estimation if a bounding box was devoid of LiDAR points. So we are checking whether the current bounding box has LiDAR points associated to it, as well as the previous bounding box. Then comes your second student assignment. So what I want you to do now is I want you to compute the time to collision based on LiDAR measurements alone. And as an input, you would take the LiDAR points in the previous bounding box, the LiDAR points in the current bounding box, the sensor frame rate, and as an output, as a result, you would fill in this variable here, which is called TTC LiDAR. Now in the next student assignment, task 3 and also task 4, they both go together. you would need to associate key point matches with bounding boxes. So currently we have bounding boxes which only have been associated a set of LiDAR points, and what we need in order to perform TTC-based estimation using the camera for each bounding box, we need a set of matched key points which are enclosed by a specific bounding box. We will look into this a bit more closely once we get to the respective task, but the basic idea here is to look at the region of interest for a certain bounding box in the camera image, look at which key point correspondences, key point matches are enclosed within this region of interest, and then take those and associate them to the bounding box, with the idea behind that we will use those key point matches to find the corresponding bounding box in the next image to associate the two bounding boxes over time. And that's the end of the fourth student assignment. And basically, that's also the end of the final project. What's happening here you will be visualizing the results. We will be looking at an overlay of LiDAR points over the image. We will have a view on the detected rectangle, which is the display of the respective region of interest. That means the detected vehicle or a truck or whatever might have been present in the image. And then we will augment the image with information about the time to collision computed from LiDAR, time to collision computed from camera, and that's the display code for the actual image. Now, as you have seen, the code is basically an extended version of the midterm project. Also, the major concepts of the last lesson, which you should know from some of the exercises, have already been implemented. So let's now move forward to the first task, which is about matching 3D objects over time using key point correspondences.